Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today's lesson is titled L'Hopital's Rule. I know it looks like it's L'Hospital's Rule, but it's pronounced L'Hopital's Rule. And this is going to be a lesson where we take a derivative concept and apply it to limits. So if you remember way back in our first unit, there were times when it was quite difficult or tedious to evaluate a specific limit. And I said, we're going to learn a way to do this much more efficiently down the road. We just don't have the tools for it yet. Well, today's that day. We have garnered those tools throughout the last couple of units with our work on derivatives, and we are now going to apply them to some limit problems. So let's jump right in. This rule, L'Hopital's rule, is going to apply when we have indeterminate forms of limits. So if you think back, we had three types of indeterminate forms. We had 0 over 0. And then we had two types that we haven't really talked about that much, infinity over infinity and negative infinity over infinity. And of course, those are going to come up when you are evaluating limits at infinity. So when x is approaching infinity or x is approaching negative infinity. We've really only focused on rational functions with those and looking at our pre-calc rules. So whether the degree of the numerator was the same, different, or the same or different than our degree in the denominator. But today we're going to look a little bit more in depth into these limits at infinity, because of course we could have a limit at infinity that isn't a rational function, right? It doesn't have to be made up of polynomials in the numerator and denominator. It could be some other type of function. So when we've worked with indeterminate forms, we know that means that the limit likely exists. We just have to do some more work to find it. And some of our strategies, well, you can pause the video and write down what some of those strategies were. We had factoring. We had conjugates. And we had trig manipulation. So those were the three main things that we would try to then use to simplify the limit so that we could evaluate it with direct substitution. So if we look at this limit below, number 3, we see e to the x minus 1 in our numerator, and we see just an x in our denominator. So we could start our evaluating process, and we would, of course, check the limit of the numerator compared with the limit of the denominator using direct substitution. And right here, e to the power of 0 is 1 minus 1, so that gives us 0. And the limit of the denominator, that's pretty clear, that's going to come out as 0 as well. So this gives us an indeterminate form. And we're left with trying to use one of our strategies, right? Well, there's no trig involved here, so we can eliminate that possibility. There's no radicals here, so the conjugates doesn't seem like that's going to be a good option. And there's nothing to factor in the numerator denominator. So none of our three big strategies are working, which means we would jump to tables or graphs to just try to estimate the limit. So we're going to do that real quick just to see what that limit looks like it is. I have the function already punched into our calculator in y1, and I'm going to graph it. And as x approaches 0, right, from both sides, it looks like that limit is approaching y equals 1. That being said, using a graph is not a proof of what a limit is, right? It's just an estimation, and we can be pretty confident that this limit's 1. But if we want to prove it, we've got to use another process. We can also look at a table real quick just to verify that it looks like it's approaching 1. So I'll start my table at 0, and we'll go up by thousandths. Go to second graph, brings up the table. And you can see from both sides, as we approach 0 from the negative side, right, the limit is approaching 1, and as we approach 0 from the positive side, the limit is approaching 1. So we can be quite confident that the limit is 1, but again, if we were asked to prove it, we would need something other than a graph or a table. So, and here's where L'Hopital's rule comes into play. What I can do, and we'll go over a formal definition of this in a second, but essentially this limit up here is equal to the limit as x approaches 0 of the derivative of the numerator, so e to the x, divided by the derivative of the denominator. And maybe it'll be helpful if I actually write in the derivative operator so you see exactly what we're doing. So we take, it's not a quotient rule, we take the derivative of the numerator separately from the derivative of the denominator. So just like that. Again, derivative of e to the x minus 1 is just e to the x. The derivative of x is just 1. Now we can try direct substitution again and see if that works. And we can see that it is going to work. E to the 0 over 1 is equal to 1 over 1, which is equal to 1. And that would be an algebraic proof of the fact that this limit does indeed equal 1, which is confirmed by or this confirms our intuition based on what we saw in the graph in the table. But let's go over a formal definition. It looks pretty straightforward, but let's make sure we have all the conditions and whatnot in place for this to occur. Okay, so limit from number 3 can be found using a new strategy, L'Hopital's rule. And again, it's pronounced L'Hopital's, so there's no hospital thrown in there. So what has to be true is that the limit in so if we're looking at the regular limit, the limit of the numerator and the limit of the denominator must approach 0. Again, that's just showing us that it's an indeterminate form. Well, if that's true, then we can take the limit of the derivative of the numerator divided by the limit of the derivative of the denominator. And if that limit comes out to be a real number, something other than infinity or whatnot, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a, again, of the derivative of the numerator divided by the derivative of the denominator. And if that's equal to L, then the original limit will be equal to L as well. So again, if you get an indeterminate form, and this also works if you get infinity over infinity or negative infinity over infinity, you can take the limit of the derivative of the numerator divided by the limit of the derivative of the denominator, and as long as that's a real number, that's going to be your answer to the original limit. Now, we will see later on that sometimes you may have to do L'Hopital's rule 2 times or 3 times or maybe even 4 times, right? If this limit right here, right, so if you take the derivative of both the numerator and the denominator and then you still get an indeterminate form when you substitute, so let's say, you still get 0 over 0, well, then you would just apply L'Hopital's rule again. And sometimes you have to apply this rule multiple times before you finally get a real number for your answer. Okay, let's check out some practice problems. And I think we're going to check out problem number 5, actually. A little bit more difficult than problem number 4. So again, we're not just going to jump right into L'Hopital's rule. We need to, again, make sure that we have an indeterminate form. So we're going to try direct substitution. So I'm going to check the limit of my numerator as theta approaches 2 of sine of pi times theta. Well, that's going to give me sine of 2 pi, which is equal to 0. Let's check the limit of my denominator. Limit as theta approaches 2 of theta squared minus 4. That's going to give me 4 minus 4, which is equal to 0. So I do get an indeterminate form. which means I can imply L'Hopital's rule. We'll say invoke. L'Hopital's rule. There are some different spellings of this. Some people spell it without the S, L'Hopital. There is some spellings with the S, so just to let you know, you may see it written some different ways. So what that means is that this limit right here is equal to the limit as theta approaches 2 of the derivative of sine of pi times theta divided by the derivative of theta squared minus 4. That's going to be equal to the limit as theta approaches 2 of pi cosine of pi theta. Okay, so the derivative of the outside function is the derivative of sine, so that gives us cosine pi times theta. The derivative of the inside, pi times theta, is just pi. That is going to be all over to theta. So now if we substitute in, I get pi times cosine of 2 pi all over 4, which is equal to cosine of 2 pi is equal to 1. So I get pi over 4. So the answer to my original limit is equal to pi over 4. All right, we're going to do 2 more. I'm going to jump down to number 6 next. We're doing number 6 because this is a limit at infinity. So we're going to show you one with the indeterminate form where it's infinity over infinity or negative infinity over infinity. As always, I encourage you to pause the video and see how far you get before we go over it. I'm going to check to make sure that the limits of my numerator and the limits of my denominator both approach something that gives us an indeterminate form. This does indeed approach infinity. The natural log function, well, if we think about what that looks like, we just sketch it out. It's a good one to know. This is 1. Even though it looks like there may be a horizontal asymptote somewhere, there isn't. It does slowly continue to increase and increase without bound as the x values get larger. So it will approach infinity as t or x approaches infinity. Check our denominator. Limit as t approaches infinity of t squared. Well, that is certainly going to approach infinity. And we have an indeterminate form. So we invoke L'Hopital's rule. It is good to write that down, again, on an AP exam if you're going to use L'Hopital's rule and it's an open-ended question. Let the reader know why you're using L'Hopital's rule, because there's an initial condition that says the original limit has to have an indeterminate form. So if you just invoke L'Hopital's rule without showing that, then you haven't showed the reader that you understand why we're allowed to invoke L'Hopital's rule. So this limit is now going to be equal to the limit as t approaches infinity of the derivative of my numerator divided by the derivative of my denominator. The derivative of natural log of 3t would be 1 over 3t times the derivative of my inside function, which is 3t times 3, all over 2t. That is equal, if we simplify, that is equal to 1 over t divided by 2t. Oops, let's make sure I carry down these limits, because you would lose points on a quiz if you didn't do that. So I have the limit as t approaches infinity, of 1 over 3t times 3 all over 2t, which is equal to the limit as t approaches infinity of 1 over t all over 2t, which is equal to the limit as t approaches infinity. I'm just showing you each step of this process of 1 over t times 1 over 2t, which is equal to the limit as t approaches infinity of 1 over 2t squared. And this is now, we could think about our pre-calculus rules here, right? We have a polynomial in the numerator, a polynomial in the denominator. So we can think of our power rules. Because the denominator's power is higher than the numerator's, this is going to approach 0. And we can also say that there is a horizontal asymptote at 0 as well. But that's not really part of the answer to this question. The answer would just be 0. You don't have to write out every algebraic step here. Like these, all of these steps right here, actually up to here. If you wanted to leave those out and just jump from this one, no, that's pretty poor. Let's redo that. Oops, there we go. So you don't have to show each step. I'm just showing you because I think sometimes it's helpful. But if you wanted to, you could jump straight from here to here. You just better make sure you know that you're doing your algebra correctly, right? Because I'd rather write out a couple more steps and not make a mistake than try to do something in my head and make a small mistake that causes my limit to be incorrect. All right, we are going to jump to number 11, I believe. That's going to be our last one. All right, so it looks pretty straightforward. It's a rational function, polynomial in my numerator, polynomial in my denominator. Let's go through and see if direct substitution produces an indeterminate form. So limit as x approaches infinity of 4x squared minus 5x. That is going to not approach 0. That is going to be equal to infinity. Remember, we only really care, as the x values get really large, we really only care about the term with the largest power. We want to see what that's doing. And in this case, that's approaching infinity, which means the entire expression is going to approach infinity. Let's check the limit of the denominator. Limit as x approaches infinity of 1 minus 3x squared. So again, we only care about the term that has the largest power. That's negative 3x squared. As I substitute in larger and larger x values, right, that term's going to approach negative infinity because of that negative 3. So this limit is equal to negative infinity, which still is an indeterminate form. So we invoke L'Hopital's rule. And again, if you haven't tried this on your own yet, go ahead and do that before we run all the way through it on video. Now you could, say what this limit is based on our pre-calc rules, right? We could look at the fact that the numerator and denominator have the same degree. So we would take the ratio of their coefficients and we should get negative 4/3 as the answer to this limit. However, again, that's not a calculus justification. That's a pre-calculus justification. So if you ever have a question like this on a free response and you're asked to find the limit, you couldn't just write down, because the numerator and the denominator have the same degree, etc. You would actually need to show that using L'Hopital's rule, the limit approaches negative 4/3, which is hopefully what we should get if we do L'Hopital's rule correctly. I am going to cross this out because we are going to need quite a bit of space here. So I'm going to start over here. This is now equal to the limit as x approaches infinity of the derivative of my numerator divided by the derivative of my denominator. So that's going to give me the limit as x approaches infinity of 8x minus 5 all over negative 6x. You'll notice, though, that this also is going to give me an indeterminate form, right? If I substitute infinity to my numerator, infinity to my denominator, this is going to give me infinity over negative infinity, which is another indeterminate form. So, invoke L'Hopital's rule again. Okay, so if you apply L'Hopital's rule and you still get another indeterminate form, you just keep going. So let's do that. So this is now equal, and I already anticipate running out of space, but we'll see. This is equal to the limit as x approaches infinity. I'm not going to write out my derivative operators again. I'm just going to take the derivative of my numerator, which would be equal to 8. Derivative of my denominator is equal to negative 6, which is equal to negative 4/3, which is what we anticipated getting based on our pre-calculus rules. You just need to note, if this was on an FRQ in a calculus exam, you would want to use a calculus justification, and L'Hopital's rule would satisfy that. One thing to note is that you don't have to write out your derivative operators every time as its own individual step. You just do need to make sure that you talk about invoking L'Hopital's rule and why we're allowed to do that. So if you show that the limit of the numerator and the limit of the denominator go to infinity, or both go to 0, or one goes to positive infinity, one goes to negative infinity, and that produces an indeterminate form, that will be sufficient enough. Your next step could just be the derivative of the numerator and the derivative of the denominator. You don't have to write out d dx for the numerator, d dx in the denominator. You can just go ahead and take that with your next step. So again, I'm doing it for the video to kind of walk you through each individual step of what we're doing. But on an exam, as long as you state why you're allowed to use L'Hopital's rule, and then that you're going to use the rule, well, then you can just jump straight to taking the derivative of the numerator and the derivative of the denominator and looking at that limit. All right, that's going to do it for this video. As always, I look forward to seeing you next time, and enjoy the rest of your day.